Hello, my name is Marcus, and today I'm going to talk about entropy and information. Now, first, I'm going to talk about generally what entropy is and what information is, and then we'll dive a little bit deeper. So, what is entropy? Well, entropy is a universal measure of randomness. In other words, it can also be seen as the measure of the amount of bits of randomness in a given system. Now, entropy can also be seen as the information that we don't have. Thus, it's the information we will gain by learning something new in a system. Uh, it shouldn't be confused, though, with the entropy that is in thermodynamics, which by definition is the information given about the evolution of an isolated system with time, which also can be seen as the measure of disorder within a macroscopic system. Now, the reason I mention this is because if we were to compare the entropy from thermodynamics with the entropy from information theory, you'll notice that their formulas are very similar. But one main thing to see, the one main difference is that with the entropy from thermodynamics, it uses a log base E, whereas with entropy, it uses a log base B, where usually B is equal to 2, which we'll explain a little later on why we choose log base 2 with entropy. So, what is information? Well, information is the change in entropy. It's the amount of bits that are being changed. Thus, information is the information we obtain by learning the value of something. So, how did entropy come about? Well, it started with a paper that was written in 1948 by a mathematician by the name of Claude Shannon. He's known as the father of information theory because he introduced this idea of entropy, which is the fundamental concept for information theory. Now, in the paper, it describes entropy kind of as the average surprise or how much you are surprised on average. Thus, it can be seen as the expected value of the information contained in a message. Now, how entropy is measured in what's called a Shannon bit, which is the quantitative measure of information or the measure of surprise. So, to understand this conceptually of what entropy actually is, consider the following example. Let's say I flip a coin, and when it lands down, I cover it immediately with my hand. So neither you nor me knows what the value of that coin is. We don't know if it's head facing up or tails. Now, thus we can say that there is one bit of entropy in this question, or whether the coin is heads or tails. Now, suppose I was to remove my hand and look down at the coin. Thus, my entropy with the coin is 0 because I have gained one bit of information. But from your perspective, since you do not know what the coin is, you still have one bit of entropy. Now, another example to help solidify this is consider the example of a poll on some political issue. Now, typically, polls happen because the outcome of the poll isn't already known, such as before a president gets elected, you want to know who might win, what's the probability of it, different things like that. In other words, the outcome of the poll is relatively unpredictable, and actually performing the poll and learning the results gives some new information that wasn't previously known. These are the different ways of saying that the entropy of the poll result is large. Now, consider the case that the same poll is performed at a second time shortly after the first poll. Since the result of the first poll is already known, the outcome of the second poll can be predicted well, and thus the results should not contain new information. In this case, the entropy of the second poll result is small relative to the first because the first time we did this poll, we didn't have any previous information to know who might win in the poll or something like that. But now that we have had one poll and we do the second poll directly after it, there's not going to be much change in the information. Yes, maybe a little, but it's not going to be a lot or a ton of new information. So, what are some general properties about entropy? Well, the entropy is equal to 0 when the outcome is certain. Thus, this is when the probability is either equal to 0 or 1. Now, the more information we obtain about a system is the more the entropy is reduced because it makes the system more predictable. Now, this can be seen in the following example. Think of if I was to go around the university and ask people what their favorite color is. When I first start out, I don't know what anyone's favorite color is, but maybe after asking 100 people or 200 people, I may start to learn and know, have a general idea of what people's typical colors are. Like, for instance, when babies are born, usually a guy's room is painted blue or a girl's room is painted pink. Well, you could probably make some estimations on, like, oh, maybe the girl's favorite color is pink or the boy's favorite color is blue, and different things like that. But it goes on when you start to ask different questions and gain more information into your system. Now, entropy can also be entropy is also used to define the measure for the amount of information a discrete random variable produces. Now, this uncertainty in the random variable or random quantity is the information you would obtain by learning the value. Some other general properties is that the minimum entropy occurs when one of the probabilities is 1 and the rest are 0. Now, the maximum entropy, on the other hand, occurs when the probabilities all have equal values, thus 1 divided by n. Now, consequently, when you move away from this equally likely outcomes, it introduces predictability, which means that the entropy will go down. Now, the fundamental idea is that if the entropy of an information source drops, that means that we can ask fewer questions to guess the outcome. Now, consider this on a smaller scale with the color question. If I was sitting with one person and I told them to guess my favorite color, or for instance, when you would drive in the car with your siblings or friends and ask 20 questions, well, every time the person asks you a question, the result set on which they can pick from has been reduced because they're gaining more information, and the more information they gain, the higher they have a chance at being able to guess the answer. So, what is entropy good for? Well, it is a good measure of the strength of a password. Thus, if you have a high entropy, you have a low predictability. And this can help in many different applications because we have password managers and password rankers, and you notice that when you create accounts on certain websites, it will rank the strength of your password. Well, entropy can be used in order to determine this strength. Now, also, it plays a fundamental role in information and communication, thus arises in the context of randomness extraction, compression, and coding. It can also be seen in message authentication and cryptographic applications that typically worry about predictability. Why? Well, because they typically will use random source information, such as from the fan noises in your computer, the mouse clicks that a user clicks, or the time between the time it takes to read and or write from disk. And the reason they pick these values is because they're random. No one particularly knows how often you're going to click on your mouse pad or how often your computer is going to read to disk, because it's based on it's different for every single person. So what is the formal definition of entropy? Well, let there be a discrete random variable x, which is an element of the set x, where x is distributed over p, distributed over a probability distribution p. Now, the entropy is defined as h of x, which is the summation over all the values x in the range of x, where we multiply the probability of each element x times the log base 2 of the probability of each element x. Now, one thing to note is that X must be a countable set. It can't be something such as the real numbers, but it could, for instance, be the natural numbers, or let's say a set of between 1 and 10. So how is entropy measured? Well, at the beginning we mentioned that it was that we use log base 2. Well, the reason we use log base 2 is because entropy is measured in bits, and typically we use log base 2 in order to differentiate between two states. And typically, when dealing with entropy, you have a 0 and 1, or a yes and no, a heads and tails, true and false, etc. Thus, there's only two states. Now, if we were to consider a system with n distinguishable states, it means that it can only register log base 2 n bits. But note, by changing the base to, let's say, 3 or 4, we will essentially change the units. Thus, the base corresponds to a source that uses n symbols to encode messages. Another thing to note is that when reading different articles about entropy, or sometimes called Shannon entropy, you'll notice that the unit of measurement is sometimes called a Shannon, or a NAT, or a Hartley. But most commonly you'll see it represented as bits. Some other properties about entropy are when it's the zero log of 0, we let it equal to 0. This is allowed because from algebra we can see that when x is approaching 0 for x log x, we can say it goes to 0. Another thing to note is that entropy is always a non-negative value for the discrete random variable x. Why? Because the probability is between 0 and 1. We're taking the log of the probability, thus it will give us a value that is less than 1. And since we negate before the summation, we will always get a positive value. Thus, we are summing up non-negative elements. Also, you have the entropy, which which says that the entropy is equal to the expected value over the distribution p of the negative log of the probability of x, where x is the random quantity that we are taking the expectation with respect to. Now, you'll notice that the entropy depends on the distribution p, where x is distributed according to p. Thus, it's common to see written in many textbooks and papers the following notation, h of p, instead of the h of x, where x is distributed among distribution p. Now, if we were to consider this distribution p from 1 to n, then we can say that h of x is equal to the summation from 1 to n for the probability times the log base of the probability for every element in the p distribution. So next we're going to talk about the binary entropy function. Now, let's consider a random variable x where x belongs between 0 and 1, and the probability is equal to 1, where the probability that x is equal to 1 is equal to p, and 0 otherwise. Thus, x is a Bernoulli random variable. Thus, we can say that the entropy for a random variable x that assumes only two possible outcomes, where one of which occurs with probability p, is the following equation. But note that the above function only applies when p is between 0, when p is an element in between 0 and 1. Thus, p must be a number. But why? Why must it be a number? It's important to note because the notation looks very similar to the previous slide, where p is a distribution, as you can see here. But this notation, which is typically used, and because they're very similar, it sometimes gets confusing. So, since x is a Bernoulli random variable, the entropy is a concave function. Thus, here you have the graph of the entropy function, where the entropy is continuous in the domain of 0, 1, where the y-axis represents the entropy and the x-axis represents the probability. Now, in the graph, you can see that the entropy is maximized when p is equal to 1/2, right about here. Thus, the entropy of 1/2 is equal to 1 bit. This can be interpreted as saying that each time we flip a two-sided coin, we get out at most 1 bit worth of randomness, and we obtain exactly 1 bit of randomness when the coin is fair. Now that we've kind of went over the idea of entropy and what it's defined as and how the different types of entropy, let's see a simple example to help solidify this. So let x be a random variable where x is the element x is in the set x, where the set is for 1, 2, and 3. Now the probability of 1 is equal to 1/2, the probability of 2 is equal to 1/4, and the probability of 3 is equal to 1/4 also. Now applying the Shannon entropy we learned just earlier, we will get the following. So you have 1/2 times the log of 1/2 minus 1/4 times the log of 1/4, and so on. And thus, you can see that by simplifying it a little further, we'll notice that the log base 2 of 1/2 is equal to 1. The log base 2 of 1/4 simplifies to 2, as can be seen on the right-hand side. And when we plug these numbers back into the formula and simplify, we'll get that the entropy is equal to 3/2. Now, in this example, the main thing you want to see is what really affects the entropy is not the elements in the set X, but it's the probability of the elements in the set X. Now, in conclusion, I want to say that entropy is the fundamental component of information theory, and it's used in communication and other different topics within computer science, such as cryptography, randomized algorithms, and so forth. And entropy is the measure of randomness in a system, which provides many useful descriptions for the long-term behavior of different random processes. Now, the entropy's behavior is a key factor in developing coding theorems of information theory. Thus, entropy is an extremely useful tool used in many fields such as cryptography, random algorithms, and much more. I hope you enjoyed my presentation. Here are the references I used to create my presentation. If you have any questions, don't hesitate to contact me. I want to thank you again for listening to my presentation.